Okay, today we start Chapter 5, Section 5.1, Angle Measure. So, a pretty long homework assignment, but a lot of them will go really quickly. A couple of homework tips for you here. Sure you've all seen it before, but you'll need to remember the Pythagorean theorem for right triangles. And also there's a 3, 4, 5 triangle that shows up in the homework, and you have to remember that that is a right triangle. Last little bit here that I'm sure you've probably seen this before, the angles for a triangle add up to 180 degrees. I think you'll need that fact in the homework somewhere too. Okay. Right, so it's such a weird thing to try to define what an angle is. It seems so weirdly formal here. We have these two rays, R1 and R2. They've got a common initial point and they just fly out into space. We call one of the rays the initial side and the other the terminal side, and the angle is the measurement of the rotation that it takes to sweep the initial side over to the terminal side. If that rotation is counterclockwise, we say that this is a positive angle, and if the rotation is clockwise, like from, what would that be, 3 o'clock down to 7 o'clock. If that's a clockwise rotation, we say the angle is negative. Okay, so that's what an angle, let's see, AOB, where did that come from? Well, we've got a point A, O maybe standing for the origin, and B is on the other ray. Okay, so the amount of rotation from initial side to terminal side is what we call the angle measure. We're going to measure the angle by somehow quantifying the amount of rotation it took to go from initial to terminal. And we've got two different measures here. One is called degree measure and the other is radian measure. Maybe I can get all of these to go at once. So the degree measure is defined by saying that a full rotation, that is all the way around, once around, is 360 degrees. So where did 360 come from? Well, probably it came from the fact that 360 has a lot of divisors. Okay, so we've got 4 angles here, this theta, and I guess I'm trying to illustrate that the green is the initial ray and the red is the terminal ray. So what I'm going to do first is try to estimate the fraction of a complete revolution for these 4 angles. So the first angle there looks like we're going quarter way around. The next angle, the second angle, looks like we're going 3/4 of the way around. The third angle, well, it looks like we've gone 1/4 of a revolution, but we've also gone in the clockwise direction. So we're going to call that negative 1/4 of a revolution. And this last one, this is why I hedged and said that this was an estimate, but I'm just going to go ahead and say that this is the fraction. It appears to be 1/3 of a revolution. Okay, so here come the degree measures for these angles now. For the first angle, all the way around is 360. That's the definition of it, of degree. And so we're going 1/4 of that. The first angle is has a 90 degree measure, has a measure of 90 in degrees. Right, so I don't think I'm going to be able to typeset this quickly enough. Maybe I can get a copy paste going here. Degree. Oops. Yeah, let me put that off screen and get it somewhere where I can copy paste it. I didn't get the copy. Sorry about this little delay. Okay, the next angle, that's 3/4 of a complete revolution. So 3/4 of the 360 winds up being 270 degrees. The next one, this is going to wind up being minus 90 degrees. And the last one was 1/3 of a full rotation. So that's going to be 120 degrees. So that's the symbol for degree, this little circle. It's a sort of a superscript. Okay, anything else? That. No. Well, that's what I said is that 360 may be chosen because it had a lot of divisors. It was divisible by 4 and divisible by 3, so we didn't have to have fractions here, so that's nice. Okay, the other way we measure the angle is through something called radian measure. So radian measure, kind of defined by this little picture here, it's the length of this arc. So the portion of the circle here, this is called the arc. And it's called the arc subtended by the central angle theta. And this happens to be the unit circle having radius 1. Okay, so the definition for radian measure is that the radian measure for this angle will actually be the length of this subtended arc. So this is kind of slightly thick and bold here. The length of this arc right there is defined to be the radian measure for the angle theta. Okay, and just you need to be familiar with this phrase, arc subtended by an angle, before you take the reading quiz, just as a heads up. Okay, so one of the things you need to remember here is the circumference of a circle. So just remember that's 2 pi r. And so we want the circumference for the unit circle. So just to make it clear here, a unit circle, when we say that, what we mean is that its radius is 1. So the circumference of the unit circle is 2 pi times 1, that is 2 pi. Okay, so why are we talking about that? Well, I want to think about doing a full rotation, going once all the way around on the unit circle. Okay, so if you do that, if you go exactly once around, then the subtended arc will in fact become the entire circumference of the circle. So in radian measure, a full rotation is 2 pi radians. So rad is an abbreviation for radians, and a lot of times we won't include that. If there's no unit given, we'll assume that the measure is in radian measure. Okay, so let's look at the radian measure. So the same 4 angles, we've already estimated the fraction of a full rotation, but now we'll go to radian measure. Okay, so all the way around in radian measure is 2 pi. So what's going on here? So this first angle, this quarter of a rotation in radian measure is pi over 2. And the next one, the 3/4 times 2 pi. Oh, you're really missing that keystroke. I think this cancels down to 3/2. It's funny to write it that way. 3 pi, it's funny to write it that way. 3 pi over 2. The next angle, again, the reminder that because of the clockwise rotation, that's a negative quarter rotation. And so this will be negative 1/4. Full rotation would be 2 pi. So this is negative pi over 2. Just can't hit that. And then this last angle, again, our estimate was that was 1/3 of a full rotation. So in radian measure, that becomes the angle 2 pi over 3. Okay. So we have these 2 measures for angles, and in trigonometry, I think degree is the favored way to measure angle. And in calculus, radian is going to be the favored method for measuring an angle. So in a pre-calculus course, you're studying trigonometry, but you're going to go on to calculus. So you really need to be able to master both of these measures and to be able to convert back and forth between them. So the easiest way to think about this conversion is to remember that pi radians is 180 degrees. So pi radians, remember all the way around is 2 pi. So pi radians is half a rotation. All the way around is 360 degrees, so half the way around is 180 degrees, beg your pardon. Okay, so if we take 180 degrees and divide it by pi radians, because these two measures are the same, the ratio here is 1. And when you multiply by this 180 over pi, you'll be converting radians to degrees. You'll cancel out your radians and you'll introduce degrees. And then the vice versa, to go from degrees to radians, you multiply by pi times 1 over 80. Okay, so convert 30 degrees to radians. Okay, so we take 30, and let's see, we want to introduce radians and get rid of degrees. So the radian measure is the one that has pi in it. So we bring in the pi, we get rid of the 180. So convert from degree to radian, multiply by pi over 180. And I think this becomes pi over 6. Right? And convert pi over 3 to degrees. So I think I mentioned this before. There's no unit given here, so we assume that that's in radian. The pi is also a very good indication that this is radian measured angle. Okay, so we got pi over 3, and this time the idea is that we want to get rid of the pi. That's at least the way I think about it, but the table or the blue box tells you this. We were going to multiply by 180 over pi. Okay, so the pi's cancel, and this becomes 60 degrees. I still have that in the copy paste. Okay. All right. So we're going to look at coterminal angles. So to talk about coterminal angles, we first talk about putting an angle in standard position. And what that means is that we're going to make sure that the initial ray is pointing out the positive x-axis. I think that's been the case in all the angles that we've looked at so far. They've been in standard position. Okay, angles in standard position that differ by full rotations are called coterminal angles. Coterminal means that their terminal sides wind up being coincident, or they coincide. Okay, so these three angles are all coterminal. It would be hard to know without the little spiral label here that this angle was actually a rotation that went once all the way around and then an additional 90 degrees. This angle went twice all the way around and then an initial 90 degrees. Okay, so these angles in degree measure are 90. Well, a full rotation is 360 in degrees, so that's 450 degrees. And then the last one, we actually added on 2 full rotations. I don't know can I do that in my head? I think that's 90 plus 720. I believe that's 810 degrees. Right? In radian measure, so the first angle is pi over 2. The next one would be pi over 2 plus 2 pi. And the third angle would be pi over 2 plus twice 2 pi. Again, full rotation in radians is 2 pi. So this would be plus 4 pi. Okay, so numerically, angles are coterminal if they differ by a multiple of 360 or a multiple of 2 pi, depending on whether they're in degree measure or radian measure. Okay, so sometimes we're given angles and want to bring them down to smaller numbers by choosing a coterminal angle to the original one. So that's what we're doing here. We want an angle somewhere between 0 and 360, that is a smaller number that is coterminal with 800. And what you do here is simply subtract off multiples of 360 until you get to some number between 0 and 360. Right? The new number will be coterminal because that's essentially the definition, that you are coterminal if you differ by a multiple of 360. So if we subtract off one multiple, I think we're down to 440, and that wasn't enough. So in fact, I think what we needed to do was subtract off twice 360, because, oops, it's supposed to be 800. This comes out to be minus 720. We get an angle of 80. Same thing here. I guess the request now is not to get a smaller number, but instead a preference for getting a non-negative angle measurement. So we want something coterminal with angle minus pi over 2, but the request is that it be somewhere between 0 and 2 pi. So this time we're going to get coterminal by adding multiples of 2 pi. We started out negative, that's why we're adding, and we're adding 2 pi because we're in radian measure. So minus pi over 2, and I think if we add a 1 multiple, we wind up in the region where we're supposed to be. This would be minus pi over 2 plus 4 pi over, oh shoot, so it looks like 3 pi over 2. 3/2 pi, so it's between these two numbers. Okay, I better timestamp here. I'm already starting to feel like this is going to run long. At, when is this? 1644. Length of a circular arc. A circular arc. So we've already seen this idea, this circular arc. This is the arc that's subtended by the angle theta. So again, this phrase for the reading quiz, make sure you kind of get it tucked away here. So this is the formula related to the picture. The length of this arc, the arc subtended by theta in a radius r circle, is given by this formula. Okay, so probably on a note card you should be probably making notes of important formulas, but just to show you real quick how you derive this formula if you forget it. Oh, I should also say that this theta needs to be in radians, so note the theta must be in radian measure for this to work. Okay, so remember the formula for the circumference of a radius r circle, so the entire circumference is going to be 2 pi r. And then what we want to look at is what fraction of the circle does the angle subtend. Okay, so because we're in radian measure, the fraction of the circle is theta divided by 2 pi. 2 pi is all the way around. We're only going theta around. That's the fraction of the entire circle. So S is the fraction of the circumference. Namely, S should be equal to, let's see, I guess we'll put the fraction number out in front. Theta over 2 pi. This is the fraction of the circle, and the entire circumference is 2 pi r. And you can see that the 2 pi r is canceling there and giving us that formula. Okay. Right, so let's put it to use. What is the length of the arc of a circle with radius 9 centimeters subtended by an angle of 5 pi over 6? So that's the type of question you're going to get on your reading quiz and on other quizzes and tests and so on. And you have to be able to come up with a picture on your own. That's why you need to know what those words mean. But so think about it, make sure you can, on your own, come up with this picture. This question is asking us to find the length of S, this red arc, on a radius 9 circle with a central angle of 5 pi over 6. Okay, well, it's scrolled off screen, but the formula that we're going to use here is simply this one. And our R is 9, and the angle is 5 pi over 6. sorry, bad typesetting here. Okay, so I guess we could cancel a 3 out of this thing, maybe. This would be 2 and a 3. So as a final answer, maybe 15 pi over 2. Okay. So I tried to say that, or remind us that this formula only works when the angle is given in radian measure. So if you're asked this question about an arc of a circle where the angle is given in degree measure, like 220 degrees, what are you going to do? Well, here's the picture. Actually, it's not the way I'd probably draw it, but this might be a homework problem where they've given the angle as 140, but the arc is subtended by this other angle. So because total rotation is 360, this must be angle 220. Right? So this red arc S here is actually the arc that we're trying to measure the length of. Oops, sorry, this was supposed to be radius 5 to match the picture. Okay, so to use this formula, we've got to be in radians. Option 1, convert to radians. All right, so we take our 220 and we multiply it by pi and divide by 180. And that puts us into radian measure. Maybe there's some cancellation there. Radian. Okay, and now use the formula. So S would be 5 times this radian measure. So 55 pi over 9. Option 2 is to sort of just go through what we did in deriving the formula. The total circumference of the circle, well, again, it's the 2 pi r, so 2 pi times 5. And then we just want to think about what fraction of the circle are we using. Okay, so we're taking 220 of the full 360 degrees. So this would be another way to come up with the formula, or the value for the length of S. So didn't multiply out the 5 for some reason. 55. So either option is fine. Okay, one more timestamp here. We're at 23. Okay, so we just talked about the oh, sorry, I skipped over. We're at 23 here. We have even further to go. Okay, so we talk about radian measure as being the length of the arc in a unit circle, a radius 1 circle. But this formula that we have just derived will now let us try to measure radian measures for angles in circles that have radius r instead of radius 1. So if we want to measure the length of S in a circle like this, we know the formula, this is one we just did, is S equals r theta. So if instead what we're trying to do is measure the angle theta, we can solve this equation for theta, and we get that the theta is equal to S over r. So this is another way to talk about radian measure. It's the length of the subtended arc divided by the radius of the circle will give you the radian measure for the angle. Examples might help. Right? Find the angle. Okay. So find the angle. It's right here, Dr. Will. I can see it. Find the radian measure of the angle. So we want to know how many radians this theta is. And if you want to minimize the number of formulas that you memorize, you might just stick with S equals R times theta and plug in. You say, okay, my S here is 10, my R here is 5, and my theta is what I want to solve for. And so this says that sorry, I think I said 5. I think I tried to type 5. It was just a miss key here. So this says that in radian measure, theta is equal to 2. This is rad. I'm going to add rad there because it's very common that radian measures have a pi in them, and so this one didn't happen to have a pi, so it's kind of important maybe to say this is radian measure. Okay. All right. One more time. This is 26 minutes now. Okay, so we talked about measuring the length of the arc subtended by an angle, and now we're going to look at measuring the area of the sector. So we want to know how much pizza we get to eat, how many square inches of pizza that this slice is made up of. Okay, so the formula is right here. The formula for the area of this slice will be 1/2 r squared theta. It's here in the great big blue box as well. And I'll derive it in exactly the same way that we talked about the length of the arc. So we do it once again as a fraction. Oh, again, as a reminder. I'm bad about this reminder. The theta must be in radians. This formula doesn't work for degrees. Okay, so the area of the entire circle, remember that's pi r squared, and then we're looking at the fraction. Because we're in radian measure, the fraction of the circle is theta divided by 2 pi. 2 pi is all the way around. We're only going theta around. That's the fraction of the circle that we get. And then the area of the circle, of the sector, is going to be the fraction of the full area of the circle. 1/2, and of course it's going to match the formula that's given in the box. But it's also a way that you might rederive this formula if you happen to forget it. The pi's cancel, the 1/2 remains, and the theta remains. Okay, so we'll use it. Find the area of a sector of a radius 10 circle that has central angle 1/2 radian. So same thing here is that you'll have to be able to, from the words, create this picture on your own. Okay, so this is what they want. They want the area of this little blob in here. Okay, not a blob. It's not a blob. It's a slice of pizza. So the formula for the area, 1/2 r squared theta. That's what we just looked at. So this is 1/2. Our radius is 10, and our angle theta is 0.5, and it was given in radians, so this formula is valid. If the angle is given in degrees, you sort of have the same options as before. Convert to radians, or else recompute as a fraction, as we did. So that has area 25. I guess let's go ahead and use the units as long as I provided them. Square centimeters. Radius 10 centimeter circle. All right, this is the last topic. It's at 29 minutes. Stay strong. So what we're going to look at now is motion along the circle here. We're going to have some object, and it's going to be moving along the circle. And in a certain amount of time, maybe like in 10 seconds, we're going to measure how far this object travels. And then we're also going to measure the angle that's swept out as we follow the object around. Okay, so there are two speeds that we talk about for this object that's moving. I guess it's just a little red dot. That's the object. They could have put a little bumblebee or something to give us an idea that that's what we're tracking. The linear speed, that's the distance that the particle travels divided by the time it took. And the angular speed, this is the Greek letter omega, kind of looks like a lowercase w. So that's the angle that's swept out by following this particle divided by the time it took. Okay, so here's our little boy. He's spinning a sling around, a 3-foot long sling at the rate of 15 revolutions every 10 seconds. So we're tracking the stone that's in this sling. So it says that this sling is 3 foot long, but I think what it means is that it's 3 feet from the center of this circle out to the stone as it moves around. And now we're asked to find the angular and linear velocities of the stone. Okay, so we've got the units here. In 10 seconds, what we need to do is figure out how much the angle has changed as we followed the stone for 10 seconds. Okay, the stone has spun around 15 times. So that means in radian measure, the angle has changed by 15 times 2 pi, or 30 pi. Okay, so the angular speed then is this total change in the angle divided by how long it took, and that was 10 seconds. So this is there's a fraction, 3 pi radians per second. I just wanted to get my units right there. Maybe I'll write it this way. 3 pi radians per second. It says the rock goes 1.5 times around per second. There's another way to think of that number. Okay, and now we want the linear velocity. So this time what we do is measure the actual distance that the stone has traveled. Right, so there's been 15 revolutions, and each revolution, the stone goes around the entire circumference of the circle. So I'm going to put in C for circumference, and then remind us that the circumference is 2 pi times the radius. So the radius is 3. So when this all washes out, I think this is 90 pi feet. Okay, so to get the linear speed, how fast the stone is traveling, we take the total distance that it has traveled, that's 90 pi, and we divide again by the time. And this comes out to be 9 pi. And the units here are feet per second. Okay. One last formula for the day, and then we're done. There's going to be a formula that connects the linear speed with the angular speed. And here it is in a nice blue box. The linear speed is the radius of the circle times the angular speed. I guess this is the only place I remember to say it, is that this omega needs to be measured in radians per time. If it's measured in degrees per time, you'll have to convert. All right, so here's just a real quick derivation of this formula. If you remember, S, the length of this arc in a radius r, angle theta, subtended arc, the S is equal to r times theta. Okay, but separating this out, bringing the r out in front, that's r times theta over t, and that's theta over t is exactly what we call, omega. So that's the derivation. And the last thing we'll do is just the boy with a sling again. The sling had a 3-foot radius. Once we'd computed that the angular velocity was 3 pi, this formula, again, put it on a note card, can now automatically give us the linear speed as well. So we don't have to recompute that. We can get it from using this formula. And with that, I'll close